Good morning, students. Finally, today will be our last discussion on uninformed search techniques. Okay, today probably we are going to sum up with all the uninformed search techniques that we are looking since many sessions. Okay, so yeah, our today's discussion will revolve around the last uninformed search technique, and yeah, afterwards we can also see quickly just discuss that what all uninformed search techniques we saw. Okay, at the end of the session we are also going to just have two visuals of what a state space look like. Okay, of course the visuals will not be too much exhaustive, okay, because it is difficult to um, place so much of different type of states, okay, in one diagram, but there will be two visuals on which can just help us to understand what will be the state spaces looking like. Okay, and we may end our discussion while seeing certain animations of what a breadth first search and a depth first search do. Fine. So let us continue. Okay, so the uninformed search technique that we are going to see today is what we call it as uniform cost search. Okay, and we are also going to see some example of state spaces. Fine, example of state spaces. Okay, it is something which is a different thing. Okay, it is something which is in general. So now let's first concentrate on uniform cost search. Okay, so I think till now, okay, we are quite aware about, okay, what do we basically want to mean by uninformed search technique, that there is we just move towards the goal state, okay, and there is nothing like a strategy, okay, basically which helps us. And the searching algorithm may traverse various paths, okay, certain paths may not reach towards the goal state, but then they just get explode. Okay, also in our previous session, okay, we looked about searching technique, bidirectional search, wherein in certain applications, if the goal states are fixed, okay, if it is known that this is the goal state and probably this is the only goal state, yeah, in that case it is possible that we can make use of bidirectional search techniques. Okay, so that's how bidirectional search was, what we call it, it was differing from rest of the search techniques that we have seen. And that is what the case today also, students. Okay, these uniform cost search, okay, that we are going to see is quite differ from what all search techniques that we have seen. But again, okay, to implement the concept of uniform cost search, either we need to take breadth first search, or maybe we need to take depth first search. And yeah, preferably, okay, at many times, okay, we prefer to take breadth first search. The only reason is because of its optimality. Okay, so when the need of optimalism is there, okay, rather than going to the end of the one path, okay, then yeah, breadth first search needs to be followed. Okay, so that is the brief concept about uniform cost search, in the sense that it is different from rest of the uniform search techniques that we have seen till now. And again, to implement the uniform cost search, we have to make use of breadth first search or the depth first search only. So now what we see from the word is it's a something, a word which is known as cost, which is written, which was not there in any of the searching techniques till now. So none of the searching techniques, okay, revealed the word cost. Yes, but students, if you remember, okay, then before we started the searching techniques, before we all started with the fundamentals of what we call searching, okay, we discuss something about like problem solving agents. And then at that time only, we also discussed about what we call it as state space. Then we discussed about what is initial cost, sorry, what is the initial state. Okay, and at that time, okay, we talked about a word which is known as path cost. Okay, and before we talked about path cost, okay, where we have seen certain examples, okay, about the vacuum cleaner agent and about other one, wherein we just tell that what is a cost of a particular move. So we what we saw is that every time we have written a value, an integer value one, which means that no matter whatever the transition of the state is, which means if it transits from first state to another state, okay, it has to perform certain action, and the cost of that action is one. Okay, so now there will be many agents in which, let's say, for every transition of the state, okay, as in from transition of state 1 to state 2, state 2 to state 3. Now when I use the word transition from state 1 to state 2, state 2 to state 3, basically what I'm trying to say is that only that I am traversing from, let's say, node wise, right? I'm going from node 1 to node 2, node 2 to node 3, which means basically I'm exploring. Okay, so that is what only the transition is. Okay, you are at a particular node or a particular vertex and then going at a different vertex. Okay, so that is the transitioning you are doing, and to do that transition, okay, some cost will be involved. Now normally in most of the cases this costs are same. Okay, which means if you traverse from node 1 to node 2, or maybe node 1 to node 3, the cost involved will be 1 only, which means the cost on both the sides to is 1. In that case, okay, cost is irrelevant. Okay, which means the traversal, okay, is basically important with respect to goal. Okay, and with respect to the shortest path, okay, which can reach towards the goal, irrespective of the path cost. Okay, but now there will be certain agents wherein if you want to traverse from state 1 to state 2, maybe the amount of cost will not be the same. Okay, so if we talk about, let's say, something like taxi driving agents, okay, and the taxi driving agent, let's say, of course it will have a goal. Okay, maybe a fixed goal, whatever it is. Okay, and then it has to continuously traverse at many different locations in between, which will be nothing but their different states. Now maybe definitely it is possible that if a taxi driving agent, okay, there are two paths available to taxi driving agent, or we can say two states available to taxi driving agent, the chances are very rare that the cost to select the state 1 and the cost for selection of the state 2 will be same. Okay, which may not be the case if we talk about a chess playing agent. Okay, so let's say chess playing agent is in one state, and then it has alternative to choose from two states. So let's say that the chess agent, okay, selects this state. Okay, in any of the state, okay, the cost is very simple. Okay, it is just one move. Okay, so the cost, it's just going to be a move. Okay, and when it is a move, okay, then there is nothing, no, we can say no extra time or no extra, because when you talk about cost, okay, either you're talking about time, okay, that you spend to take that action and to transit to that state. Okay, or maybe some other resources. Okay, so if we talk about a taxi driving agent, then yeah, probably the time consumption, then some another other parameters will also be there. Okay, maybe the energy consumption of the taxi driving agent, okay, maybe a bit more. Okay, as compared to one state and another, but that will not be the case if we think about a chess playing agent. So there will be, students, what I want to say over here is that there will be many examples wherein the transition from one state to another state, or the transition from one node to another node, will take the same amount of energy, will take the same amount of time. Okay, we are not talking about the whole path right now. Okay, I'm just talking about a transition from one state to another state. Okay, so in most, we can say, in most of the examples, okay, it may take the same amount of time. Okay, if it is taking the same amount of time, then that is a very simple case of, okay, either you use breadth first search or depth first search. Okay, and there is nothing like uniform cost search into picture. So yeah, uniform cost search can also be there. Okay, but then it will be just equivalent to what we call it as either a breadth first search or a depth first search, depending on whatever search strategy we implement. But on the contrary to it, if to transit from one state to another state, okay, the cost taken is more. Okay, there is a difference in cost, then yeah, in that is the case of what we call it as uniform cost search. So yeah, students, with this note, okay, with this we can say initial description on it, we start looking what exactly we want to say by uniform cost search. So uniform cost search is different from breadth first search and depth first search, because here the costs come into play. In other words, traversing via different edges might not have the same cost. So that's what we just told right now, that when we traverse from different edges or different states, okay, the cost is not the same. So now the goal is to find a path where the cumulative sum of cost is least. Okay, now what do we mean by cumulative sum of cost? Okay, we are starting from the root node and we have to reach towards a goal state. Okay, and the cumulative, okay, cumulative means, let's say, the cost from, let's say, root to node 1, then from node 1 to node 2, node 2 to node 3, node 3 to node 4, node 4 to node 5, and let's say node 6 is the goal node. So that is the cumulative cost, okay, of all the nodes from the root nodes, and the last node may be nothing but the goal node, okay. So what is the cost of node is nothing. Cost of node, which means here the node that we are talking about is nothing but our goal node, is equals to the cumulative cost of all the nodes from the root. And what will be the cost of root node? Of course, the so every time, okay, when this uniform cost search will start, okay, the cost will always be zero because of, it's starting from root, okay, so there is no cost, okay, it has not started its journey yet. And then it will sum up, we can say, all the cost of all the nodes, okay, that it is traversing, okay. And what is the goal of this uniform cost search? Okay, so basically, the uniform cost search, now there are two things, okay. So one thing is that okay, the goal state or something like this is aware of, okay. But what uniform cost search, okay, it's the performance, or what we can say the property of uniform cost search is basically not to reach towards the goal state, or find it search in such a way that the goal state is achieved or something like that. This basically will be used more wherein, okay, we are looking for a path, okay, which is costing the least, okay, rather than actually searching something, okay. So we are looking for a path, okay, when we talk about the uniform cost search. Fine, let's go ahead. So uniform cost search is a searching algorithm used for traversing a weighted tree or a graph. Okay, whenever you say a weighted tree or a graph, which means every edge has a certain weights associated with it, certain costs associated with it. This algorithm comes into play when different cost is available for each edge. The primary goal of uniform cost search is to find the path to the goal node which has the lowest cumulative cost. Uniform cost search expands node according to their path cost from the root node, okay. So now normally the expansion will be according to the cost, okay. So again, it is an uninformed search. Why? Because see, let's say what happens, okay, that there are three paths available to the uniform cost search, and let's say it selects a path, okay, which is having the least cost, okay. It has done its job, okay, it has selected a path which is having the least cost. Not necessarily that these path only may lead to the goal state, okay. And that's why these uniform cost search still belong to a category of what we call it as uninformed search, okay. Because the path selection is of course done into a situation wherein when the cost is lowest, okay, but that it's not guaranteed that that path is going to lead towards the goal state, okay. So there can be two scenarios. If the goal state is known, okay, then totally it is a different story. But if the goal node is not known, okay, the uniform cost search, okay, the purpose of it will not be to search towards the search or search the goal state, basically to find a path, okay, maybe in such a way that while the traversal of entire path towards the goal node, the cost should be less, okay. But then how it will select the path, okay, it from one node it has to transit to another node, okay. So to do that transition, basically it will make use of the cost which is lying onto that path, okay. Yeah, so what we see an example over here is that so there are certain nodes that are given to us, okay, levels. We already know what do we mean by levels, and now what we see, okay, the only difference in this diagram is, okay, we have already seen many diagrams like this, okay, but the only difference in this diagram is that whatever we see is that in uh, you know all the nodes are connected by, or all the nodes which are connected have different cost involved, okay. So if you want to transit from S to A, okay, the cost involved will be 1, and if you want to transit from S to B, the cost involved will be 4, okay. Then from A to 3, the cost involved is 3, and then from A to 2, the cost involved is 2, okay. So something like that, okay. And yeah, because in these diagram it is told that G is nothing but the goal state, okay. Then the traversal is shown that S, from S it will first select 1, after 1 it has options to go to 3 and 2, so it will select it 2, and from there it has option to go to F, okay. The cost of F is not written, okay, but somewhere it will be 5 or something like that, okay, 4 or 5, okay, any value which is greater than 3, and that's why 3 is being selected, and and that's how it has reached towards the goal state. Now in this diagram, okay, the goal state is specified, okay, but that may not be the case always, okay. If the goal state is not specified, the uniform cost search, okay, will start running, okay, depending on the minimal cost path. So yeah, it may at times happen, okay, that the goal state is somewhere over here, and what has happened is the uniform cost search has run according to its performance, that okay, I want to run on the least cost path. So it has started running, but it has ended over somewhere, okay, where the goal state is not achieved, okay. So then it has to again start visiting maybe the other alternative nodes, okay. So what basically happens, it will use breadth first search, okay, or it is going to use depth first search, okay, mostly breadth first search more, and it will keep storage of all those nodes, maybe which were having the higher paths, but it will not traverse to that nodes, okay, it will not visit that nodes, okay. So what we know in breadth first search also, okay, we keep information about all the nodes, okay, that the possibilities. So let's say if we are on S, we keep information about A and B, okay, but then yeah, it is on us, okay, that which we want to explore. So then we select A, and then and then what we call is that we want to just visit the members of A. Okay, so that's why it goes ahead. So what it will do is basically it will store two information. It will store node and it will also store its path. Okay, so that information will be stored, but then it will visit only that node and that path. Okay, which is less. Okay, so that's how basically the working of uniform cost will happen. So now what we see over here is that, okay, insert the root into the queue, okay. So we may use some data structure like queue while the queue is not empty, okay. I think this is the same data structure that we have used in breadth first search also, okay. But now there is some difference over here, okay. So insert the root into the queue while the queue is not empty, dequeue the maximum priority element from the queue. Now if priorities are same, okay, so let's say it might happen priorities are same, which means everyone is having the same path, okay. Then in that case, okay, simply alphabetically a smaller path is chosen, okay. If the path is ending in the gold state, print the path and exit. Else insert all the children of the dequeued element with cumulative cost as priority, okay. So now in that case, okay, the priority, okay, what the maximum priority will be given to a node or to an element whose cumulative cost is less, okay. So it is vice versa, okay, the cumulative cost should be less and that element will be given the maximum priority. Now what exactly the cumulative cost is, that also we have to understand. So let's say when we store information about S, and what will be the value of the cumulative cost stored? 0. When we insert about, let's say, A, okay, the cumulative cost will be 0 plus 1, so the cumulative cost will be 1. When you insert information about D, it will be, let's say, 0 plus 1 plus 2. So actually D will be having a cumulative cost which we called it as 3, okay. And when you insert information about G, it will be something like 3 plus 3 equals 2. So now we are going to probably so, and that will the same will happen for the other nodes also. So now what you have to do is you have to select an element, okay, which is having the lowest cumulative cost, and that lowest cumulative cost will be given the highest priority, okay. So then maximum priority element from the queue, but who will have the maximum priority, okay. So while inserting the children, okay, of the dequeued element, so let's say if we talk about S, now S is having A and B, okay. So of course S will be dequeued, okay, and then now you have an option on either the traversal should begin from A or should begin from B, okay. But now while you have stored the information of A and while you have stored the information of B, basically you have also written their cumulative cost with it, okay. And in that case, next time after S is already selected, okay, whenever it wants to basically select the next element, okay, then it has to either go for A or B. But then what it will do is it will dequeue the element. So now next from A or B, it has to either choose A or B, but then that it will choose depending on the cumulative cost, okay. So the least the cumulative cost, the maximum the priority, okay. So that's how, okay. So can make use of a data structure which is known as priority queue. So the only advantage of using priority queue is that, okay, that you can give priorities, okay, while all the elements are getting inserted into that queue. and that's why okay we can come to know. So while we insert an element, and if it's, let's say, cumulative cost is less, the priority of that will be given more as compared to the other element which is getting inserted whose cumulative cost is more. So that's how the whole concept of uniform cost search may work, and it will start picking up all the we can say all those elements whose cumulative cost will be less, or ultimately we can say whose priority will be more. Okay, and then it has to do this process until and unless the goal state is found, and once the goal state is found, it will print the path, and we can easily calculate the path cost. Okay, so this is about uniform cost search. Again, let's see the algorithm first. Okay, insert the root into the queue. While the queue is not empty, dequeue the maximum priority element from the queue. If the path is ending in the goal state, print the path and exit, else insert all the children of the dequeued element with cumulative cost as priority. Fine. So the advantages of uniform cost search is that it is very optimal at every state because the path with the least cost is chosen. Disadvantages is that it does not care about the number of steps involved in searching and only concerned about the path cost. Very important. If we are not aware about the goal set, okay, the uniform cost search is not at all concerned about searching or moving itself towards the goal state. Its concern is only about path, okay, and the chosen node or the chosen state, okay, will only be having a dependency of the path, okay, nothing more than that. Okay, so that's where, okay, but yeah, at every state path, okay, at every state, okay, the uniform cost search is very optimal because given 4 5 alternatives from one place, okay, it will always select a state, okay, which is in the most optimal category. Okay. um, Now let's say if the path cost is same, okay, if it is 1 1 1 1 1 everywhere, then uniform cost search is nothing but it is just equivalent to breadth first search. Okay, so yes, that is about uniform cost search. Okay, it works on a parameter which we call it as cost. Okay, then there is something like cumulative cost of the node, that is nothing but, let's say, the cost of the node starting from the root node. And then it works on a concept wherein, okay, what it does, it makes use of something like a priority queue, and it gives priority of that element to be maximum whose cumulative cost uh, uh, from the root node is as less as possible, and then it traverses its journey according to the tag, and then it stops at a place where the goal node is being reached. Okay, so yes, students, okay, this is about uniform cost search. Okay, so by this, okay, we can say that yes, we have understood about uninformed search techniques. Okay, and we started with breadth first search, then we saw about depth first search, then we saw an additional feature to depth first search, that is IDDFS, iterative deepening depth first search. Okay, uh, then we also look upon the concept of bidirectional search. So bidirectional search was something, either with the help of breadth first search or depth first search you can implement. But yes, we have seen that why using breadth first search it was very optimal, and why if we use depth first search, the bidirectional search may actually go parallel into different directions, and it may take a lot amount of time for them to meet at some juncture. Okay, so that was about bidirectional search, and yeah, today what we saw is about uniform cost search, when the searching mechanism basically works on the cost which is involved in the process of transition from one state to another state. So yes, students, that was about uniform cost search, and now, as we already discussed, we are going to see something about what is state spaces. Okay, so now these whole searching techniques are revolving into state spaces basically. Okay, there will be a big number of state space, and then the search has to start its journey over there from maybe certain initial state, and has to reach towards the goal state, or maybe just traverse the state space. What is that state space? Okay, so today, in very layman terms, okay, this diagram is there which can also tell you in the most layman terms, and also I will also try to tell you a definition of a state space, okay, in the very layman. Okay, first of all, just we are talking about state space. Okay, searching is something after that. Okay, now when you talk about state space of, let's say, any AI agent, or maybe anything, okay, that you want to make it into working. So state space is nothing but all the different possibilities of that of that particular application, or maybe of that particular scenario in which the AI agent is going to work. Okay, so here we have taken an example of a tic-tac-toe game. Okay, and what we see is that it is nothing but it is having, let's say, 3 plus 3 plus 3, that is what we call it as, let's say, 9 blocks. Okay, now one thing is that we should be able to aware about that what is true and what is not true. Okay, so what is true? True is that if a space is empty, then x or 0 can be a part of it. So that is something which is true. Okay, if we talk about chess, okay, then what is true, what is not true is that we know that, okay, these, let's say, these small player, okay, onto a chessboard can only move in this direction. Okay, so let's say they can only take one step, or they can just take 2.5 step, or they can just go in a vertical direction, they can just go in a horizontal direction. So that is true. And maybe certain other behaviors of it is something which is not true. So that consideration should be there into your mind before we make the state space, because it will talk about every possibility which is true. That is also very important. So now, students, if you look at the diagram, okay, what we see over here, it is a tic-tac-toe, okay, and the initial state, okay, in this case, it is given that it is completely blank. And let's say one player is starting and the player has been given X. Now, over here, of course, limited possibilities are shown, but you can just visualize what will be the first level of possibility. From these initial state, how many different states are possible? Okay, so yes, we can say 9 different states will be possible. So we can say the very first level of branching is 9. Okay, why? Because either X can be over here, or maybe over here, or maybe over here. Second, X can be over here, here, or here. Third, X can means, so this is already first, second, third, fourth, fifth, sixth, seventh, eighth, ninth. Okay, so just in first possibility, let's say X is over here. The second possibility will be X is over here. The third possibility will be X is over here. The fourth possibility will be X is over here. The fifth possibility, X over here. Sixth possibility, X over here. Seventh possibility, X over here. Eighth possibility, X over here. Ninth possibility, X over here. Okay, let's say depending on let's say any search algorithm. Okay, again, let's say we'll talk about search algorithm afterwards. Okay, we are just talking about state space right now. So now we know that that will be the first move. Okay, so and now let's say if the first move is this, if the first move is this, and we already know that in that case, once an X player has taken a move, the next move has to be by 0. So let's say given this possibility, what are the possibilities of 0? So now there is only one restriction for 0, that it cannot put 0 over here, because that is something false. So true will be X being over here, 0 being over here. Okay, from this one state only, what are the possibilities, students? I'm talking about given X over here, 0 over here, then given X over here, 0 over here, given X over here, 0 over here. Okay, given X over here, 0 over here. So let's say keeping the stagnant position of X, okay, 0 has now 8 different possibilities from this state space. Now let's take a scenario where instead the X was being kept over here instead of the first place. Again, in that 8 different possibilities. So 8 different pictures in which the game would be there. Again, let's see if we talk about a position of X from over here, then again 8 different possibilities. So fine, you can understand that the number of sub branching which has came from this node. Okay, now let's take about this condition. Okay, so now there will be turn of X. So the state space will look like all the possibilities given X position, given 0 position, what will be the third position of X? So all the possibilities of that. Okay, same with another scenario, same with another scenario, same with another scenario, same with another scenario. Okay, and that's how the state spaces will go on increasing and increasing. Okay, and that's how the state space search, the state space, basically not search, okay, the state space of tic-tac-toe will look like. And yeah, we can imagine it will go into thousands and thousands, and yeah, more than that. Okay, so that many different possibilities of these 9 squares given the position of X and 0 will be there. Now, when the search starts, it will start with this. Okay, and let's say your AI agent is X, and let's say any opponent is 0. The AI agent, now have to start its journey into the state space. Okay, and to decide where it has to go. Okay, the AI agent, okay, is just going to use this state space at its knowledge. Okay, it will see that, okay, I am at 0, I am at X, and the other position on the board is 0. Then it will select from all the alternatives that now at which alternative it wants to go. Okay, and let's say if it is uninformed uninformed searching technique, then basically it will just keep on traversing. So yes, another example of a state space, okay, what we see over here is an a puzzle game, okay, wherein this is, let's say, the scenario, and what we know about the puzzle is that the either the blank space we can move on left, right, up or down. Okay, so that, let's say in this case, okay, there was having two possibilities, okay, so sorry, three possibilities, because down nothing is there. So either you can put blank over here, or blank over here, okay, or blank over here, and that's what the possibilities are shown. Now let's say if an agent has picked up this possibility, then what are the possibilities again? So either one can come over here, okay, or maybe seven can come over here, so that possibilities are shown. Given this possibility, okay, one can come over here, four can come over here, eight can come over here, or six can come over here. Given this scenario, okay, so what you can see, this goes on and on and on and on until and unless, okay, after all the shifting we reach to a scenario which is nothing, which is equals to our goal state, which is not yet defined into it, because the state space is going to be extremely wide. Okay, so if you keep moving this, maybe at some position into the last level of the depth, you may arrive at a situation where basically you get your goal node. Okay, but that is again a different story. Okay, the state space has to keep on making themselves more and more and more, with all the possibilities, okay, which we can think of. Okay, and while this development of state space, there will definitely be certain situations. Okay, so yeah, it might be possible, okay, that on many parts the goal node will be there. Okay, but then it depends upon the situation of an agent, on how it works and what searching mechanism it uses, and then it reaches towards the goal state. Okay, so yes, students, these was about state spaces. Okay, so today we learned about what is a uniform cost search, and also we had a understanding of what these state spaces look like. Okay, taking an example of a tic-tac-toe state space, and also the state spaces of a puzzle game. Fine. Okay, so yeah, that was there for today. Okay, and by that, okay, we have already it came up an end to what we call it as uninformed search techniques. Okay, so thank you all of you.